Hi everyone and welcome. In today's video we are going to cover the axiom of completeness. This is the very important property that distinguishes the set of real numbers from the set of rational numbers. This is what makes the set of real numbers complete. So let's recap the story so far. We have seen that the set of rational numbers, while they're very useful and nice to work with, they have some limitations. Most notably, they have gaps or holes. And that's a problem because we would like every meaningful length or quantity to correspond to a number and vice versa. However, as we have seen, the diagonal of a unit square has length square root of 2. And we saw that the square root of 2 is not a rational number. So within the context of the rational numbers, there is no number that can represent the diagonal of the unit square. And this issue becomes even more important in our study of real analysis, because very soon we are going to start studying sequences, and specifically sequences that seem to get closer and closer to some value. And when this happens, we want to be very confident that the value that that sequence is approaching is actually a number and not just some missing point or hole in the number line. And so to fix this, we extended the set of rational numbers to a larger number system, namely the set of real numbers, to fill in all the holes and gaps left by the rationals. But now, how do we actually capture this idea of no gaps in a formal or mathematical way? So far, we have seen that both the set of rational numbers and the set of real numbers are ordered fields, which just means that we can add, subtract, multiply, divide, and compare numbers in a very nice and logical, consistent manner that we have actually been doing for a very long time and taking for granted. So in this sense, the set of real numbers and the set of rational numbers, they're actually very similar, right? So what actually distinguishes these two sets of numbers apart? What new property does the set of real numbers have so that it finally makes the number line fully complete with no holes or no gaps? And the answer to this question is something called the axiom of completeness. The axiom of completeness is what makes the set of real numbers complete. It states that every non-empty set of real numbers that is bounded above has a least upper bound in R. It might not seem like it, but this is the property that mathematically captures that the set of real numbers form a complete number line with no holes or no gaps. And this is the key difference between the set of real numbers and the set of rational numbers. In fact, we will very shortly show that the set of rational numbers do not have this property. There are subsets of rational numbers that are bounded above, but do not have a least upper bound in Q. In case you have forgotten what the supremum or least upper bound is, you can check out my previous video which explains all about these concepts, but I will do a quick recap here. So the definition of a supremum is the following. A real number U is the least upper bound for a set of real numbers if it satisfies the following two properties. Number one, U must be an upper bound for A. And number two, it should actually be the best or the tightest upper bound. It should be the least upper bound. That is, if U naught happens to be an upper bound for A, then our upper bound U is actually less than or equal to U naught. It's the most tightest upper bound or the least upper bound. So this is the definition of a supremum. In this case, we actually write that U is the supremum of A. And so now coming back to the axiom of completeness is basically saying that if you have a set of real numbers that's non-empty and bounded above, well then you can further refine that upper bound. You can actually find the best or the least upper bound, and that least upper bound will always be a real number. It will exist as a real number. And so as we will show very shortly, the set of rational numbers do not have this property. There are subsets of the rational numbers that are bounded above but do not have a least upper bound in Q. But just before we do that, I would like to mention two important remarks. As I mentioned, the axiom of completeness is one way to express the fact that the set of real numbers form a complete number line. In other words, they have no gaps. But it turns out that it's not the only way to assert this fact. There are other mathematical statements that are logically equivalent to it. For example, later on in the course, we will encounter something called the monotone convergence theorem, which says that every bounded monotone sequence converges in R. While these ideas all capture the same underlying notion of completeness, we have to choose one as our foundation or starting point. And in this course, we will take the axiom of completeness or the least upper bound property as our starting point. The others, like the monotone convergence theorem, will be proven later as theorems or results that follow from the axiom of completeness. But the key takeaway is that all of these mathematical statements express the same essential truth about the set of real numbers, which is that the set of real numbers form a complete number line with no holes or no gaps. And the second important thing to note is that the axiom of completeness is not something we can derive from the field axioms alone. If you recall, when we were discussing ordered fields, I mentioned that from the 10 ordered field axioms we can derive a lot of basic facts and properties of the rational numbers and the set of real numbers that we have been using for granted. But we cannot derive the axiom of completeness. It is indeed something new, something additional that we need to assume in order to go from the set of rational numbers to the set of real numbers. Moreover, if completeness could be proven from the 10 ordered field axioms, well then the set of rational numbers should also be complete. But we will now show that this is not the case. So let's suppose, for contradiction, that it was possible to prove the axiom of completeness from the 10 ordered field axioms. So what this means is that every ordered field should satisfy the axiom of completeness because it's just a property or a result that follows from the 10 ordered field axioms. In particular, the set of rational numbers should also satisfy the axiom of completeness. But now let's show that this is not the case. Let's show that the set of rational numbers does not satisfy this to get our contradiction. I would like you to consider the following subset of the rational numbers. It's the set of all rational numbers whose square is strictly less than 2. Now the first thing to note is that this set S is non-empty because 0 is a rational number whose square is less than 2, right? 0 squared is equal to 0 and that's less than 2. So that implies that 0 must be a member of this set S. And secondly, S is bounded above by many numbers. In particular, it's bounded above by 2 because if R is an element of S, well then its square is less than 2. And since 2 is less than 4, we can square root both sides of this inequality and we get that R is less than 2. So what we see is that 2 is indeed an upper bound, right? 2 is bigger than or equal to everything inside S. But now we're assuming that the set of rational numbers has the axiom of completeness. And so since S is non-empty and is also bounded above, it should have a supremum. The supremum of S should exist and it should do so as a rational number. But if you take another look at this set S, what is the supremum of this set? Well, we know an upper bound for this set is 2, but we can do better than that. You can check that, for example, 1.5 is an upper bound. So is, for example, 1.42. And I hope you can see that the actual least upper bound of this set is actually the square root of 2. It's a number satisfying whose square is exactly 2. Now this claim is something we would need to prove formally, and we will do this in a future video, that there is a number whose square is 2. There is in fact a real number whose square is 2. But for now, I hope you can at least see that it is at least plausible that the supremum of this set is a number satisfying whose square is exactly 2. But now this is an issue because in a previous video, we have proven that there is no rational number whose square is 2. And so this implies that the supremum of S cannot be a rational number. And so this is a contradiction. In fact, for any rational upper bound, we can always find a smaller rational number that is still an upper bound. And so therefore, the set of rational numbers does not satisfy the axiom of completeness, and from which it also follows that it's not possible to prove the axiom of completeness using the field axioms. Because if it was, then Q should satisfy the axiom of completeness, but we've just found a subset of the rational numbers that's bounded above and it's non-empty, but actually has no least upper bound in Q. And so I hope this convinces you that the axiom of completeness is indeed something special, something extra that the set of real numbers has, but the set of rational numbers does not have. This is the distinguishing property that makes the set of real numbers a complete number line with no holes and no gaps. Now we can finally give a definition for the set of real numbers. Up until this point, we have been pretty hand-wavy and trying to intuitively understand what the set of real numbers are, but now we can make this a little bit more formal. So the set of real numbers is an ordered field that also happens to satisfy the axiom of completeness. In other words, the set of real numbers is an ordered field in which every non-empty set that is bounded above has a least upper bound in R. And so this is the formal definition that we will be using in this course. And as you can see, it's something more than just an ordered field. It's an ordered field plus the axiom of completeness. Let's end this video with a neat problem. You might be wondering, why is the axiom of completeness stated in terms of least upper bounds or supremums and not in terms of greatest lower bounds or infimums? Could we just as well define completeness using infimums? And the answer to that question is actually yes. There is an equivalent version of the axiom of completeness which states that every non-empty set of real numbers that is bounded below has a greatest lower bound or an infimum in R. But the thing is, we only need to assume one of these versions as an axiom. The other one can actually be proven from it as a consequence. So we don't need to assume both as separate axioms. And so as an exercise, let's actually prove that every non-empty set of real numbers that is bounded below has an infimum, using the axiom of completeness as we stated it earlier using supremums. To begin the proof, we will let A be a subset of real numbers that is non-empty and also bounded below. And now we will define a new set, let's call it B, and this set B is actually the set of all lower bounds for set A. Or more precisely, it is the set of all real numbers that are less than or equal to everything in A. And here's a helpful picture. In orange, let's say we have our set A. Notice that A is non-empty and it's bounded below. It might not be bounded above, it might go on forever here, but the key is that it's bounded below. And the set B is shown here in blue. It's the set of all lower bounds. And our goal is to show that the infimum of A actually exists. So we can see that the infimum of A would be a point right over here, somewhere over here, right? And the main tool at our disposal is the axiom of completeness, which is a statement about upper bounds and least upper bounds. And the key to notice here is that the supremum or the least upper bound of all the lower bounds is a candidate for the infimum of A. So I'll say that one more time because this is very important. The key to realize is that the infimum of A, which is the greatest lower bound for A, is actually the supremum of all lower bounds. And so we will show that the infimum of A exists by showing that the infimum of A is actually equal to the supremum of B. To complete this proof, we actually need to show three things. The first thing we need to show is that the supremum of B exists as a real number. Next, we have to show that this real number is indeed the infimum of A, which requires showing two conditions. So let's begin by showing that the supremum of B exists. To show that it exists, we will want to invoke the axiom of completeness. And so for this approach to work, we have to show that B is non-empty and also it is bounded above. Well, since A is bounded below by assumption, what that means is that there is some lower bound for A. And since B is the collection of all lower bounds for A, it must have that lower bound of A. And so therefore, B is non-empty. Next, let's show that B is actually bounded above. And to do this, we will pick an arbitrary element in A. And we can do this because A is non-empty. Then what do we know about the set B? Well, the set B is a set of all lower bounds, right? So that means that B must be less than or equal to A for all B and B. And so A is actually an upper bound for B. Now let's consider what's special about the members of A. If we go back to this helpful diagram, notice that from B's perspective, the members of A are all upper bounds. So since the set A is actually upper bounds for B, what we have is that for this particular A that we picked, it is an upper bound for B, right? So A is actually greater than or equal to everything in B. And so A is actually an upper bound for B. Since B is non-empty and bounded above, it follows by the axiom of completeness that the supremum of B must exist and it must do so as a real number. Now we can show that this number is indeed the infimum of A. And to do that, we need to show two conditions. The first condition we need to show is that this number acts as a lower bound of A. To show this, let's begin from the perspective of B. As we've discussed, all the A's act as upper bounds for B. And since the supremum of B is the least upper bound, it must be smaller than or equal to all these A's, right? So what we get is that since the supremum of B is the least upper bound of B, it must be less than or equal to any other upper bound. In particular, it must be less than or equal to all the A's. So we have the supremum of B is less than or equal to all the A's because all the A's are upper bounds for B and supremum is the least upper bound. So it should be less than or equal to all the members of A. And now let's shift our perspective back to A. What we see is that this number, the supremum of B number, is actually a lower bound of A, right? Because it's less than or equal to everything in A. Next, let's show that the supremum of B number is actually the greatest lower bound of A. To show this, let's suppose that B is some lower bound for A. Well then, this lower bound should be a member of the set B because B is the collection of all lower bounds for A. So in terms of the picture, we've just picked some element here. Now from the perspective of B, the supremum of B is an upper bound for B. So it should be bigger than or equal to everything in B. In particular, it should be bigger than or equal to the selected B. But now let's shift back into the perspective of A. What we have just shown is that if I pick any lower bound of A, then this number is actually greater than or equal to that lower bound. In other words, this number, the supremum of B number, is actually the greatest of all lower bounds. And that actually completes the proof that the supremum of B is indeed the infimum of A. We have shown that the infimum of A, or the greatest lower bound of A, exists just by using the axiom of completeness. And so as a quick summary, what we see is that given the axiom of completeness, it turns out that every non-empty set A that is bounded below also has an infimum. And this is because the infimum of A, or the greatest lower bound of A, can be defined in terms of the supremum of the set of all lower bounds of A. And so therefore we don't actually need to assume the infimum version separately, because it just follows logically or as a consequence from the supremum version. And so that brings us to the end of this video, where we explored the axiom of completeness. This is the very important property that distinguishes the set of real numbers from the set of rational numbers. In the next video, we will explore something called the nested interval property. This is another perspective on what it means for the set of real numbers to be complete or have no gaps. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.